sounds good to me.
So yeah, hello everyone. It's my great pleasure to have David today here. David did his PhD in applied mathematics in Cornell. He then started to work as a senior research scientist at Uber, and most recently he switched to a senior research scientist position at Facebook. Apart from that, David was one of the main organizers of the NeurIPS 2020 Black Box competition. And yeah, has a range of papers on Bayesian optimization, and which he's hopefully going to present today. So yeah, with that, floor is here.
Yeah, thank you so much for the introduction and for inviting me. So yeah, I'm a research scientist at, I guess it's Meta now, as of a few months ago, as part of the adaptive experimentation team. And the focus of this talk will be on some of our most recent work on high-dimensional Bayesian optimization. Let's see, does that work? Yeah. Okay, so the layout of this talk looks as follows. I'll give a short introduction to Bayesian optimization, high-dimensional Bayesian optimization. So I know many of you have seen this before, but I promise it will be pretty brief. And after that, I'll talk about our work on Sparse Axis-Aligned Subspace BO and SAASBO. And then I'll show a use case at Meta where we were using SAASBO and some of our multi-objective methods to tune a large-scale production model and actually, ship that into production. And then finally, I'll discuss some of our work on multi-objective trust region Bayesian optimization, which we're using for example, AR see-through display design. So in a nutshell, Bayesian optimization looks something like this to the right. The goal is to optimize a black box function f of x, where f is assumed to be expensive in some sense. This could be expensive in the computational sense. Evaluating f simply takes a lot of time. It could be hours, it could be days. It could also be that it's expensive in a monetary sense or opportunity cost. But there is a particular reason for us to want to limit the number of times we evaluate this function because it's expensive. And we assume that f is like truly black box. We have no additional information such as gradients. So given an input x, I query that and I get just a scalar output back, no other information. The way Bayesian optimization tackles this problem is by leveraging two things. The first thing is a probabilistic surrogate model, which given all of the inputs and outputs of this black box function, we fit a model to help us fill in the gaps and help us make predictions for inputs that we haven't yet tried. It is important that this probabilistic surrogate provides both mean predictions and some form of uncertainty. And using this probabilistic surrogate model, we then have an acquisition function that is responsible for trading off exploration and exploitation to avoid local minima and lead us to the global optimum of this function. So if you look at the figure to the right, you can see like roughly what a Bayesian optimization looks like. We take our input data D, we fit this probabilistic surrogate model, then we optimize our acquisition function to select one or maybe even a whole batch of candidates. We then take these candidates, we evaluate our black box function f, we get some new data, we update our surrogate model, and we repeat this procedure until our budget has been exhausted. When it comes to the surrogate model, we often use a Gaussian process. They're very convenient to work with since we have analytic posterior distributions. So we can not only just predict a mean for a test point, we can predict an entire Gaussian distribution, and that gives us the mean and uncertainty that we want to leverage in the acquisition function. And these GPs require a covariance function that tells us the similarity between two points x1 and x2. And if you look at the bottom left, you can see an example of such a covariance function, the squared exponential. And one thing I want you to pay attention to that will become relevant in a couple of slides is the length scale that appears in the denominator here. So ideally, we want parameters that aren't important to correspond to larger length scales, which means that those dimensions are averaged away. So that is like a way for the Gaussian process model to regularize away parameters that aren't important. But in a high dimensional setting, that proves to be more difficult than one would have hoped. And then if you look at the bottom right, you can see some draws from a Gaussian process prior and some draws from a posterior when we have condition on some data. Okay, so high dimensional Bayesian optimization is a lot harder than the traditional applications of Bayesian optimization to the low dimensional setting. And many methods do really well for problems with maybe 10 or 15 tunable parameters. But if you take a vanilla Bayesian optimization method, you try to apply it to a 100-dimensional problem, you'll see that it doesn't work very well. And there are many reasons for why it doesn't work well, because the problem is a lot harder. So going from 10 to 100 dimensions doesn't just make the problem 10 times harder. The search space grows exponentially with the dimensionality, so the problem becomes much harder than that. So generally, to get sample efficiency in a high dimensional space, it requires making some additional strong assumptions on the structure of the function we're optimizing, or potentially use a large number of function evaluations. This talk will discuss both of these approaches. In the low dimensional setting, we can assume that once we have collected enough data, our Gaussian process model becomes so accurate that it knows where the global optimum is. But obviously in a 100-dimensional space, that just can't happen. We will never be able to collect enough data for the model to become that accurate. So we need to find a way to work around that and get good optimization performance, even if our Gaussian process model makes pretty poor predictions in large regions of the space. And continuing on that point, Gaussian processes are very good at interpolating. So like making a prediction in between two test points or in between two training points is rather simple, but they are not as good as extrapolating away from the data. So in a high dimensional space, there's a lot of extrapolation that's necessary because we don't know much about the behavior at the boundary. That leads to the Gaussian process making predictions with large uncertainty, simply because it doesn't know what's going on at the boundary. And some of those points can be very tempting to the acquisition function, but often do not result in discovering good solutions. And there are many common approaches to HDBO, and this list is not meant to be exhaustive, but I just wanted to mention a few common themes that are very popular. So the first one is assuming that the function we are optimizing has low dimensional linear structure. Methods here include ELBO, HASBO, and REMBO. The main idea is to assume that our function f is actually just a low dimensional function if we apply the right linear projection to the inputs. And failure modes with these approaches is that f may not actually have the structure, and then these methods may not work very well. And even if they do, we probably don't know what phi and the subspace and dimensionality is. And these methods are often very sensitive to these choices. A second theme that is pretty popular is assuming additive structure. So we assume that our function f actually decomposes into a sum of low dimensional functions that allows us to use an additive kernel to fit our GP and then solve independent acquisition function optimization problems and then concatenate the candidates. Failure modes here are that additive structure is usually not a realistic assumption. At least in my experience, this usually doesn't work very well. And even if additive structure is a good assumption, learning what the decomposition is rather hard since it's probably not known beforehand. And then a third theme is some form of local optimization, like turbo, where the idea is to restrict the area in which we optimize the acquisition function to avoid uncertain points that we don't believe are going to be good. And failure modes here is that turbo may not converge as fast as some of these other methods if some of these assumptions are correct, and also since turbo is designed for a high throughput setting. Okay, so that's my intro. So I'll move over to talk about our work on SAASBO. This is joint work with Martin at the Broad Institute. And the setting for this work is a large number of tunable parameters. We want to tune potentially a few hundreds. And we have a small number of function evaluations, at most a few hundreds. So this requires a method that is very sample efficient. Okay, so in this work, we take the view that the poor performance of Bayesian optimization in this setting is that the surrogate model is not good. And I already tried to make this point a couple of slides ago. So if we can just come up with a surrogate model that is more suitable for these high-dimensional spaces, then we can just use any acquisition function like EI and hopefully get good performance. So something you can observe if you take some high-dimensional data and feed a GP is that even though we hope that many of these length scales that aren't corresponding to important parameters are set to large values, it doesn't really happen. It's two things I think can explain that. One is that the regularization is not strong enough. And the second one is that in a high dimensional space, there just isn't enough evidence to like truly remove a parameter. But that's something that we aim to change here. So the assumption that we are making, and as I mentioned a few slides ago, in a high dimensional setting, you need to make some sort of assumptions on the function f to be able to be sample efficient because the problem is so much harder. So our assumption is that the input parameters exhibit some hierarchy of relevance with a large number of parameters actually not being important at all. So for example, we have this 100-dimensional space. It could be that x3 and x52 are crucial. We need to tune those and tune those very, very carefully in order to find good solutions. So we need to have a Gaussian process model that is aware of that and discovers those two parameters so we can tune them appropriately. And then it may be that we have another group of 4 parameters, say, that they are of moderate importance, like setting them appropriately will help us. They're not as important as these other two, but if we can tune them appropriately, then that will help. And then maybe in this particular example, we don't need to worry about any of the other parameters that actually do not affect the black box function. So we are targeting functions that have this structure, and this is a structure that I've observed is often common in practice, that even though people want to tune 100 things, it actually boils down to setting the right handful of parameters to the right values. So our approach is to place sparsity inducing priors on the inverse length scales to identify the most important parameters. And in particular, we do this by having 2 half-Cauchy priors. We first have this global shrinkage parameter tau that is parameterized through a half-Cauchy distribution. And then our inverse length scales also follow a half-Cauchy distribution of this sample tau. Half-Cauchy is a natural choice here as the distribution concentrates at 0. And we do prefer setting the inverse length scale to 0 because if you don't really know if a parameter is important or not, we will just assume that it's not important. But the half-Cauchy distribution has heavy tails. So if there is strong evidence in the data that a parameter actually matters, then there is enough mass in the prior to pull these inverse length scales away from 0 and this parameter to be kept. The role of the global shrinkage is to control the overall model sparsity so that when we have very limited data, we don't let too many inverse length scales escape 0. But once we collect more and more data, more and more inverse length scales can escape 0. And if you think about the example on the previous slide, maybe when I have 10 or 20 data points, I only expect to discover these 2 really crucial parameters. But then as we go, hopefully I will discover like some of the remaining 4 in that second group that are also of importance. And to do inference in this model, we use Hamiltonian Monte Carlo, as we found it to work much better than map estimation. And specifically, we use the no U-turn sampler for approximate Bayesian inference. And we use the resulting posterior samples to compute the acquisition function via Monte Carlo. So let's look at some results. We study 3 high-dimensional real-world problems, and there was a hyperparameter for the half-Cauchy distribution of this global shrinkage parameter tau. We set that to 0.1 for all problems, and I've never really changed it since. And for all problems, we used the expected improvement acquisition function, as our point was to show that if we fix the Gaussian process model, then Bayesian optimization will just work. On the top plot, you can see the mean function values versus the number of evaluations. And you can see that on a 100-dimensional rover problem, on a 388-dimensional SVM problem, and what I think is a 124-dimensional vehicle design problem. I'm blocked by my own little Zoom screen here. You can see that that SAASBO performs very, very well across these three problems. If you look at the bottom row, you can see the distribution of the best value found across replications. And looking at these distributions is quite interesting because you can see that on the rover problem, it's a lot harder, and many of the methods do have replications where they don't find very good solutions. But on average, SAASBO does better than the other methods. If you look at the SVM problem, you can see that SAASBO is very, very consistent here, and the variance between replications is very small. It finds the global optimum or something very close to the global optimum every time. And here, like other methods like HDBO does well in some instances, but in some other instances performs worse than random search. So this additional robustness is very appealing, since in practice we can only apply these methods once, not 30 times. And if you look all the way to the right, you can see the performance on this vehicle design problem where SAASBO is followed by Turbo and CMAS. Okay, so one thing that I think is very appealing with this prior, and this is also by design through this global shrinkage parameter, is the adaptivity of it. So if you look at the figure to the right, you can see the effective subspace dimension defined by the number of median inverse length scales that are larger than 0.1. So that will be the number of median length scales below 10. And you can see that early on, SAASBO mostly focuses on tuning 2 parameters, but then as we go, more and more parameters are discovered to have some form of importance, and their length scales are also allowed to be set to something that's a bit smaller. So this adaptivity is nice, that the whole goal of this model is to not overfit. So by keeping too many inverse length scales from escaping 0, we can kind of control this overall model complexity and make sure we make progress with our optimization. Okay, so as I mentioned a few slides ago, we observed much better performance using HMC and NUTS for doing inference. So one reasonable question to ask might be, what happens if we just apply Bayesian optimization with NUTS and don't use the SAAS prior? So this figure shows that doesn't work very well, and the performance in these high dimensional settings is coming from the SAAS prior itself. Okay, so to wrap up this section, we have seen that Gaussian process models defined on sparse axis-aligned subspaces strike an attractive balance between flexibility and parsimony. We have seen that SAASBO can quickly identify the most important tunable parameters and enable sample-efficient high-dimensional Bayesian optimization. And we have seen that SAASBO performs well on several challenging real-world problems with as many as 388-dimensional tunable parameters. So just to outline a couple of limitations with this method, other methods may be better if the function we are optimizing is known to have, for example, linear structure. The use of HMC and NUTS comes at a high computational cost. So SAASBO may not be suitable for high throughput setting, given a large evaluation budget. And frankly, I wouldn't use it for more than 100 or 200 function evaluations, because then the overhead of the model fitting becomes pretty significant. And finally, the SAAS prior may not work well if all parameters have similar or potentially identical importance. This is often the case for many synthetic problems like ACLI and rastrogen, but I'm yet to run into a setting in practice where this shows to be an issue.
A question. So do you need to run this MCMC after every new data, after every new decision? Is that what you do, or do you only run it now and then?
We run it after every time we update the data. You may not have to do that, but that's what we do.
Okay, cool. Yeah.
That would be one way to kind of cut the computational cost, right? But yeah, we aren't doing that.
Another question is, so you've showed the number of kind of the effective number of dimensions. How do these dimensions change? As in, how does the kind of exploration of the dimensions look? Does it stay at kind of still selecting always the first? It's the same set of 2 dimensions, or how quickly does it find these?
Yeah, that's a very good question. I have a figure for that. There's a figure in the supplementary material of the paper, but Usually like the first like 1 or 2 parameters are very consistent. Like the method figure or the model figures out that like these are the 2 that like I really need to nail. But then what comes after varies a bit because it may not really know. At one point it might think that like, oh, X7 is really important. And then it learns that like, no, I think it might be X19 that's supposed to come next. So it kind of alternates a bit like after like the first 2 or so. But the really crucial ones are always picked up, at least for the problems I've seen. But that's a really good question.
Nice. Thanks.
Okay, cool. So I wanted to talk about an actual use case at Meta where we applied SAASBO and some of our multi-objective work that has been spearheaded by Sam and also by Max and Nathan. So the goal here is to tune a large-scale natural language understanding model. And these are commonly used by conversational agents in mobile devices and smart speakers. Their objective is to take a user expression, for example, what is the weather in San Francisco, and convert this into some sort of structured form that can be fed down and understood by downstream tasks. So if I said that sentence, what is the weather in San Francisco? Ideally, this would be broken down into, the goal is to get the weather, and where we're getting the weather, we're getting the weather in San Francisco. And yeah, this model has a pretty complex architecture. There's a non-autoregressive model for the on-device parsing and depth-wise convolution with weight sharing. So our goal here is to tune 24 different hyperparameters of this model. And you can see them in the table to the right. There are 3 smaller feed-forward neural network type things here that we decompose into layer widths and number of layers. So that allows us to just tune everything as ordinal parameters. And the goal here is to maximize the evaluation accuracy or validation accuracy for this model, as well as minimizing the on-device latency when we actually take this model and deploy it on an actual device. And these are indeed computationally expensive. They can take anywhere from 10 hours to almost an entire day to train. So we use a batch size of 16 and asynchronous function evaluations to both combat this variance in runtime and to try to lower the overall ball clock time. And these measurements can be quite noisy, especially the on-device latency measurements. Even though they're averaged over many latency measurements, there can still be significant noise in these measurements. So when using Bayesian optimization, we need to deal gracefully with this noise. So since we want to optimize 2 objectives, we will use multi-objective optimization. So rather than optimizing a scalar function, we will now optimize a vector-valued black box function. And typically in the setting, there's no one best solution that maximizes all objectives, but there's rather like a set of solutions that are not dominated by any of the other solutions. And as an example, you can see in the bottom right, where the 3 red points are the points on the Pareto frontier. This includes the point with the best value in objective 1, the best value in objective 2, and then a third point here in the middle that is not dominated by any other solution in both objectives. So our goal is to discover this set of non-dominated solutions. And there are various approaches, such as evolutionary algorithms, like NSGA2, which is probably the most popular option. But there are also methods, Bayesian optimization methods with random scolarizations, and also Bayesian optimization methods based on hypervolume, which is what we'll use in this work. So the 4 pieces we're putting together is the Bayesian optimization friendly parameterization of the search space, where we treat everything as an ordinal parameter. We'll use SAASBO to handle this 24-dimensional search space. We will use the Q and EHVI acquisition function, which is developed by Sam and Max and Eitan, which both handles the noise and also handles the large batch size that we need in this work to lower the overall wall clock time. And then we will use an automated, fully asynchronous remote deployment of jobs. And that is our solution to tackle this particular problem. So here are some results. So while for a paper, we would have obviously wanted to run further applications, in this setting that was not possible. we were able to run Bayesian optimization and then a control on the side with just random search to have something to compare to. But these are the only 2 replications we have. So, but you can see in the figure to the right, Bayesian optimization did a pretty good job at exploring these trade-offs and was able to lower the latency of this model pretty significantly. So here, the production model corresponds to 1-1 because we have we're showing all the metrics relative to the production model. And you can see that Bayesian optimization was able to drop the latency by a lot and also slightly increase the accuracy, while using random search didn't really find anything of interest. And using SAASBO for the modeling was like a key component in this work. So here are some leave one out cross-validation plots where we fit a model to all but 1 data point and then predict on our test point just to see how well our model does out of sample. And all the way to the left, you can just see like a standard map Gaussian process, which really struggles to learn anything about the accuracy metric. But if you look at the second figure from the left, you can see that the SAAS model does a much better job at uncovering a signal in this metric, even though these are noisy measurements. So it's hard to nail this exactly, but it is learning enough for us to see good optimization performance. If you look at the third figure from the left, you can see the latency predictions for like a standard map GP. And you can see that here it's like learning a little bit, but it's like heavily overfitting and doesn't really understand like when latency is low and when it's high, even though it's like picking up some clusters. And if you look all the way to the right, you can see that the latency predictions for the SAAS model are quite good. Okay, so that was the end of that section. Any questions?
Yeah, one quick question. So you those priors, but you could actually apply them for any GP-based Bayesian optimization methods, like also multi-fidelity approaches or anything like that, right? So you don't make any assumptions here on I don't know, kernel whatsoever.
You mean the SAAS priors? Yeah, I mean,
yeah. It's just a hyper prior for the length scale, right?
Yeah, exactly. It's just to encode this idea that if we don't have strong evidence that a parameter matters, please set the length scale to something large. That's like what's encoded in the prior. So you should be able to apply that in many other contexts.
I would have another question. So for this application, how expensive was this actually? Because, well, NAS, there is a lot of different methods. There's one-shot models, there's zero-cost proxies, and so on. And a typical question there is, how does the black box optimization actually relate to the one-shot and so on? How many function evaluations did you need?
We ended up doing like 150 or so, and the evaluation time here varied between like 10 hours and roughly a day, and that was pretty heavily parallelized. So it was pretty expensive to run these. Mm-hmm. So our quota could squeeze in like a Bayesian optimization run and then like a random search run, and that was pretty much it. So, but it sort of the idea here was to show that like Bayesian optimization can be used in this setting because often it's not competitive for these NAS problems because there are much better methods. This was a very BO-friendly search space since they were hoping to tune many of these ordinal parameters, and the architecture was pretty simple.
Yeah, it was pretty BO-friendly. I think actually most NAS spaces are very BO-friendly, much more so than the typical NAS researcher would say. But still, most of these here were architectural hyperparameters that you could use in a one-shot model. So I'm wondering how well the one-shot model would do. And of course, you wouldn't have done that because that would be a lot of work. But and probably the code is not available, right? Because otherwise we could throw it into NASLib where we have tons of different one-shot models and could actually do values like that.
Yeah, so all of the code for the method is available in Axe. The actual NLU model, though, is not. So you can compare.
And that's perfectly fine. That's not expected. It's an internal matter, I think. Cool. Okay. Thank you.
Yeah, thank you.
Hey, hi. I have a question more on on the other few examples that you've used for evaluation. So you mentioned something about SVM and that optimization problem had like 300 different parameters they tuned. I'm just trying to understand, like, if let's say using this method, what kind of what kind of problems have you tested? And so you mentioned that oftentimes there is this assumption that holds that only a subset of hyperparameters is relevant. I'm just curious to learn a little bit more. If you can share what kind of problems have this kind of structure.
Yeah, that's a good question. So I can't speak too much about like internal applications without getting that approved first. But yeah, so there have been like a variety of machine learning hyperparameter tuning problems where this is often true. Like even though teams want to tune every single hyperparameters they have in their model, there are some parameters that we know are going to be more important than others, learning rate being one of them. But in a lot of cases, like it's unlikely that every parameter matters. There are going to be, some that are more important, but I'm sure there are use cases where this method doesn't work as well. But I've had a lot of luck with it so far. And then Max, I think you've had your hand up a while.
Yeah, I mean, just to talk on what you just said, yeah, and things like online experimentation, right, running kind of like ranking configuration optimizations. This also works there pretty well, because often you have a lot of parameters and teams don't really know exactly how they affect things. So we've got a lot of success with that as well. I guess the reason I raised my hand initially was to kind of like give a couple of points towards the cost of this approach for this NAS setup. I think this is not the end of the road. We can do a lot more here. For instance, right now we're just running the evaluation without really looking how well it's doing. So we could do some early stopping. We didn't really do that there just because of some infra limitations. And the other thing is, it's an interesting setup of decoupled evaluations where essentially, once you've selected an architecture to measure the latency, those are being done, on an actual device benchmark. So there's like a little room where people are measuring things on devices. That is actually relatively cheap relative to the training job of the whole network. And so what you can do is you can just evaluate a bunch of those pretty cheaply, get a good understanding of like the model for that latency, and then kind of like, save a bunch of compute by looking at things that are more interesting down the road. So there's a lot of kind of like improvements I think you can make to this.
Yep, very interesting application. Thank you.
Yeah, thank you. And yeah, Frank?
Yeah, thanks. I have one more completely different question. In these high dimensional spaces, what's your experience? Do people have a prior expectation about which of these parameters might be more important than others? So could you have user priors over where the optimum probably lies, and maybe they're completely flat sometimes and fairly peaked at other points? Or is this really, you have no idea?
Yeah, I think that's a really good question. I think this varies, but I think in a lot of settings, people do have an idea of what parameters matters. But sometimes they are wrong, and they get very concerned when like the model changed something that they didn't think was important. So that's a really interesting connection, I think, to sort of like try to encode this prior, but also not trust the user too much, because they may actually not know, because reasoning about the 100-dimensional space is quite hard, and Gaussian processes are much better at this than we are. But based on experience, I'm sure like there are some priors that could be encoded and combined with this prior. I think that would be really interesting.
Cool. Yeah. Thanks.
All right, thank you. So here's the last section of this talk, which is going from this very low evaluation budget, sample efficient setting to more of a high throughput setting, and also to do multi-objective optimization. So yeah, this is our MORBO method, which is joint work with Sam and Max and Eitan. And we are targeting, once again, tuning a large number of parameters, potentially a few hundreds, but different from a few sections ago, we now have access to maybe 10,000 or 20,000 function evaluations. So we can't afford, something like HMC because we need to have a method that also has high throughput. And also to be able to lower the walk-up time, we need a method that can handle large batch sizes, a couple of hundreds at least, and also asynchronous parallelism. So similar limitations to the single objective setting. The majority of multi-objective methods targets these low dimensional domains with 10 to 15 parameters at most. And we are targeting several hundreds. And as I already mentioned, like this SAASBO QN-HBI method from the previous section does not really apply here since it's too computationally expensive, and we need something that is much cheaper and has lower overhead. So our contribution to solving problems of this form is our MORBO method, which is like the first scalable multi-objective method that is actually practical for these high dimensional problems with thousands or tens of thousands of function evaluations. And just to motivate why we need to solve these problems with Bayesian optimization, in 2018, Mazda released its benchmark, where the goal is to tune 222 variables that correspond to properties of structural parts in their vehicles. And the goal is to minimize the total vehicle mass summed up across these three vehicles, Mazda 3, Mazda 6, and Mazda CX-5. And they also want to maximize the number of parts that are shared across the vehicles, which is a way of lowering manufacturing costs by having to manufacture fewer parts. And then in addition to these two objectives, there are another 54 black box outcome constraints that encode performance and safety requirements in these vehicles. And this problem was solved on what was at the time the world's fastest supercomputer in more than 3,000 CPU years. So if we can apply Bayesian optimization to solve these problems and be more sample efficient, then that would be a high impact on cutting this waste of compute that was needed to solve this problem. And to talk about some use cases at Meta, MORBO is used for multi-objective optimization for designing optical systems for augmented reality see-through displays. And some of our internal testing and benchmarking shows that MORBO is 20 to 50 times more sample efficient than methods like NSGA2, which are quite popular. And we use AX, our open source software, and asynchronous function evaluations on a cluster with thousands of machines to handle these large batch sizes that MORBO offers. Okay, so there are a couple of key ingredients in this method. The first one is to use Region BO, which has been like a popular approach to this high throughput, high dimensional Bayesian optimization approach. So similar to Turbo, MORBO uses multiple rectangular trust regions. They expand and shrink during the optimization based on progress. And similar to Turbo, these trust regions will mitigate the issue of overexplorations in high dimensions since we only optimize the acquisition function within the trust region. And this helps avoid fitting like a large global model, which improves computational scalability. And to support outcome constraints, we will borrow the constraint handling from the SAASBO method that can support many constraints and as many constraints as we need for this particular master problem. So one obvious thing to do would have been to just take in Turbo out of the box and just put a Chebyshev scalarization on top of it, and then hopefully that will work. It doesn't work very well. And the main reason for this is that multi-objective problems are a lot harder than single objective problems. In the single objective setting, we only need to find one good solution. And in Turbo, trust regions run completely independently. They don't share any data. And while that might be a waste of information, because the single objective setting is so much simpler, that is still like a reasonable thing to do. But now when our goal is to discover an entire Pareto frontier, this leads to this weird behavior that like two trust regions might explore, almost an identical scalarization, and we miss discovering like some parts of the Pareto frontier. And you can see that in the figure to the left here, where none of the trust regions actually ended up exploring like the top part of the Pareto frontier. But instead in MORBO, the trust regions, they share data between each other and they collaborate and try to jointly find the best breeder frontier as possible. And you can see here that like one trust region is targeting the top region, and then one is targeting more of the middle, and one is targeting like the bottom right. So this collaborative behavior is necessary in this multi-objective setting because it's so much more challenging. Key component number 2 is this data sharing and local modeling. So as I mentioned in Turbo, the trust regions are independent optimization run. They share no data between each other. And that means that each trust region on its own will try to, uncover the entire breeder frontier, which just isn't feasible since it probably requires visiting very, very different parts of the search space. So instead in MORBO, the trust regions do share data between each other, and they do collaborate, and they so since they do share the data, we don't want to use all available data to fit these models for each trust regions. We only use the data that falls into a larger trust region of size 2L. And you can see here on a very challenging problem with disjoint breeder frontier that the trust regions end up exploring different parts, and exploring these different parts here requires like zooming in on very small regions of the input search space. And you can see that the different trust regions end up going to different regions, and that allows us to like uncover the entirety of the breeder frontier. But each trust region on its own could not have uncovered these like 3 different pieces. And then the last key ingredient is our batch selection. So we want to scale to large batch sizes of at least a few hundreds. So we can't really use any prior hypervolume based methods since they don't really scale to this high throughput setting that we're interested in. So we're going to use Thomson sampling, similarly to Turbo and SAASBO, and we will do this on a discrete set of candidates. So the way we do it is as follows. To select the first candidate in the batch, we draw a Thomson sample on a set of discrete candidates, and then we pick the candidate that has the largest hypervolume improvement according to this one sample. Then to select the second candidate, we will draw a sample on another new set of candidates plus the point we already selected for the batch, and then select the second point that jointly with this candidate we have already selected improves the hypervolume as much as possible. So this gives this like nice batch diversity where the candidates in the batch are jointly trying to cover the entire breeder frontier as much as possible. And you can see this in the figure to the right, where the first chosen candidate in the batch in blue is targeting one part of the breeder frontier. The second chosen candidate in orange is targeting another part of the breeder frontier, and then the third chosen candidate in green is targeting another part of the breeder frontier. So this gives like a nice coverage and hopefully like explores the entirety of the breeder frontier.
So I have a question. So I'm confused with fully asynchronous. To me means I don't have to do batch selection. I mean, I can, so your backend allows you to, whenever something is available, you feed it one more thing, right? Which is more efficient than select batch. So I don't understand why you select batch here.
Yeah, so in practice, evaluations might like not come in the instance they finish. So they might like come in like as a group. It doesn't mean that, that we just get one at a time, but we might, fetch finished candidates like every couple of minutes or so. And
yeah, but do you think that's a good thing to do? Because I'm wondering why people always do that, right? I mean, if you have an asynchronous system, the best thing you can do is to feed it whenever anything is free. And I'm just wondering why people are getting always so obsessed with these batches, right? Maybe you can tell me, because I mean, you usually once you do a batch, that means that some people have to wait, right? So I just don't really. I mean, you're saying fully asynchronous, but then you select batches. I don't really. I mean, that's synchronous, right? Because you, I mean, while you send your batch, some of these. Yeah, I don't.
I mean, it's a reasonable question to ask, but every time you want to generate new candidates, it requires fitting a new model, and you probably don't want to do that all the time. So I think it makes sense to have like a little bit of a delay in like when you generate new points. I think if your batch size is 500, then whether you select like one at a time or 10 at a time, I don't think that will affect the performance like too much. But I also see, Max, you have your hand up.
Yeah, just a couple of responses to that. One is there are actually quite a few settings in which you need batches to run synchronous. You still have a bunch of batches that you can sequence, but you need a bunch of trials in the batch. That's especially important if you have field experiments where the actual response is non-stationary and you have to do some kind of multitask modeling across time because whatever you're running on the actual system is going to be changing. So you can't actually like do the asynchronous thing. In the fully asynchronous thing, you do have to condition on the points that you're currently evaluating, right? So it's not just about generating a batch, but it's also if you're sending out a new point, you have to take into account what things are already running on the system that you haven't yet in your training data because you don't have an observation yet. And I guess part of what this slide is trying to say is that by doing that, you can easily do that in this approach.
Yeah, good, but I just think that's easier, right? So I'm always wondering why people always go for batch and then make the problem harder than it is. I mean, I can deal with latent variables, right? I just sort of sample values for them. I mean, that's called fantasizing. That's people do this since a long time. So I just wonder why people always get so get into this batch setting, which sometimes is the case, but it's usually, if it's not, I would also not make it. Anyway, maybe it's.
Yeah, agreed. And kind of in the spirit of that, maybe we can move on. I guess my point is that, this conditioning is useful for both the asynchronous and the batch case if you do a sequential greedy case. So.
Okay. So moving over to some results. MORBO works fine on some small problems. I don't recommend using it for these low dimensional problems because other methods are better, but it's like pretty competitive on this vehicle safety problem to the left, and it works a bit better on the welded beam problem here to the right. The reason why it works better on the problem to the right is that the constraint handling from SAASBO is very good, and it works better than some of these competing methods. Then if you look at some larger problems, you can see a 60-dimensional trajectory planning problem to the left, one of these optical design problems for AR see-through displays in the middle, and then this master problem to the right. And you can see that MORBO performs well across these 3 different problems. On the middle problem, we could only run the other baselines for 2,000 evaluations, and some of them took an entire week per replication to get there. So it was quite hard to run. But you can see that even after 2,000 evaluations, they're not even close to the performance of MORBO after 2,000 evaluations. And if you look all the way to the right, we could only run random search and NSGA2 on this master problem due to the large number of input parameters and the large number of constraints. And you can see that MORBO performs much better than NSGA2 on this problem, and it corresponds to roughly a 6.5x improvement in sample efficiency. And then let's look at some Pareto frontiers. So one nice thing with this hypervolume based acquisition that we're doing is that it needs to very nicely well-covered Pareto frontiers. So you can see that this is the worst Pareto frontier discovered by MORBO when it comes to hypervolume, then the median according to hypervolume, and the best according to hypervolume. And you can see that they're all very densely covered. So a decision maker here would have a lot of things to choose between, and it does a very good job at really discovering the trade-offs between these 2 objectives. And if you compare to NSGA2, you can see that the Pareto frontiers actually never cross. So there isn't really anything on the NSGA2 Pareto frontier that would be of interest compared to the MORBO Pareto frontier. Okay, so that was all for that section. So to wrap up, we proposed MORBO, which combines trust region BO with hypervolume-based exploration, data sharing, local modeling, and asynchronous batch selection. And it sets a new benchmark for the high throughput optimization setting for high-dimensional multi-objective problems. And some limitations of these methods are that using hypervolume scales poorly in the number of objectives. This can potentially be mitigated by using approximate hypervolume computations, but it makes it challenging to apply this to more than, say, 3 to 5 objectives. And then if observations are noisy, then center selection becomes challenging, which is also the case for turbo and also the case for SCBO. And this method is optimized for the high dimensional, high throughput setting. So other methods likely will perform better on smaller problems with small evaluation budgets where sample efficiency is required. So yeah, thank you all for listening. We've considered high dimensional Bayesian optimization with SAASBO. If you're interested in this, we have a tutorial in AX, and it's on its way to BOTorch. Will hopefully be there in a couple of weeks. There's a blog post, there's a UAI paper that you can check out. For the multi-objective NAS, the method is in an AX tutorial. We have a blog post and then a workshop paper on this work. And then finally, we are working on open sourcing MORBO in both BOTorch and AX, and there is a preprint on archive that you can check out. So yeah, thank you for listening and happy to take some more questions.